Stokes theorem, very important. So the statement is, if f vector is continuously differentiable vector point function and S is a surface bounded by the curve C, then this line integral is equal to this surface integral, where the unit normal vector n vector at any point of S is drawn in the sense in which a right-handed screw would move when rotated in the sense of description of C, right? So suppose the surface S of integration be given by r vector to be equal to f vector uv, where this uv is the point in this D, the plane D, right? And its image is formed in the surface S. So if I'm having the point uv in D, then its image, that is f vector uv, is present in the surface S. So there is a one-to-one correspondence between this point and this image, right? So the surface S arises as the image of certain region D of UV plane. So there corresponds one and only one point in S. So let's write this, where this UV represents a point in a plane. Therefore, the surface S arises as the image of a certain region D of UV plane, right? So there corresponds one and only one point in S, right? For the point UV in D, there is a point F vector UV in S, right? The image of this point in S. Now we have to take the boundary of D and also the curve which is bounding the surface S. So let's K be the boundary of D and C is the curve bounding the surface S. And important to note here is that their sense of description is same. If K is in this sense of direction, then C is also to be having that sense of direction, mentioning these arrows in the same direction. So it's written, let K be the boundary of D whose sense of description corresponds to that of curve C bounding surface S. Let's start with the first part of this proof. For that, we have to take f vector to be f1 I vector plus f2 j vector plus f3 k vector, where f1, f2, f3, these are the components of the vector f. Then what is curl of f vector? It is partial derivative of f3 with respect to y minus partial derivative of f2 with respect to z plus partial derivative of f1 with respect to z minus partial derivative of f3 with respect to x, and writing here j vector, plus partial derivative of f2 with respect to x minus partial derivative of f1 with respect to y, and writing here k vector. And now I need to take the surface integral of curl of f vector, its dot product with n vector ds in the next step, right? For that, let's recall one remark, a very important one. The surface integral of f vector dot product with n vector ds is equal to the double integral over the surface S, and here we are having f1 dy dz, that is the first component of f vector, plus second component of f vector dz dx plus third component of f vector dx dy. So let's use this result first. So therefore, the surface integral of curl of f vector dot product with n vector ds, this is equal to the double integral over the surface S. Okay, what is the first component? It is this one, right? And then we have to write dy dz plus, and here dz dx plus double integral over S curl of f2 curl x minus curl of f1 curl of y, and writing here dx dy. Is it okay, fine? Okay. In the next step, I need to write the value for these. what is dy dz? Let's recall. dy dz is equal to the partial derivative of yz with respect to uv du dv. Right? So using this result now, so for dy dz I'm writing partial derivative of yz with respect to uv and then du dv, right? Plus second term and writing dz dx to be partial derivative of zx with respect to u and v du dv. Similarly writing for the third term also. So for dx dy, I'm writing partial derivative of xy with respect to uv du dv. Now this uv point is in the region D, right? So now writing this double integration over D. The integration is now with respect to du dv. So replacing this s with d, right? Okay. In the next step, we are going to multiply this inside with each term in the bracket. So this is curl of f3 by curl y, partial derivative of yz with respect to u and v. And then I'm having minus curl f2 by curl z and multiplying the same. Right? Plus, then I need to multiply this with curl f1 by curl z and then with curl f3 by curl x. Plus, I need to multiply this with these two, taking everything in bracket and writing outside du dv. I need to collect the terms with f1 first. So collecting these two together. So this is double integration over d. Writing these two together. And now collecting the terms having this f2, these two, plus collecting the terms having this f3 and taking this complete integrand and outside we write du dv. Very fine? Yes? Please mark this as 1. And now in the next step, we need to find the values of all these three terms in the integrand. First, let's find the value for this first term in the integrand. If I interchange this z with x and x with z, then I get here the negative sign. So this is curl f1 by curl z and writing here partial derivative of x and z with respect to u and v. Is it fine? Writing the second term as it is. Now I'm having this x with z, I'm having this x with y. I also need to have this x with x. With curl f1 by curl x. Because I know that this is equal to 0, so I can add this term. Let's move on to the remark. We have used this first remark and the second remark also. Now the time for this third remark. The partial derivative of yz with respect to uv is equal to this. For the special case, if I am having the same variables in this, that is xx, what I get, partial derivative of x with respect to u, partial derivative of x with respect to v, minus partial derivative of x with respect to v multiplied with partial derivative of x with respect to u. So these two cancelled out and I'm getting this to be equal to 0. This is what I have used in the third term here because this is coming out to be 0. So I can add this to these two terms. And now let's write the values for these. Partial derivative of x with respect to u into partial derivative of z with respect to v minus partial derivative of x with respect to v into partial derivative of z with respect to u. Similarly, I'm writing the other ones also. You don't have to cancel them, okay? I need to use these. We need to collect the terms now. I need to collect the terms with curl x by curl u and curl x by curl v. So collecting the terms with first curl x by curl u, what are those? So the terms involving curl x by curl u, let's collect all those terms. And when collecting the terms, please keep in mind that we must have curl z in the opposite directions. Likewise curl y, and also curl x, right? When collecting the terms with curl x by curl u, right? Similarly, you need to take care of this with curl x by curl v also, right? Okay, let's collect the terms. So here I am having curl z and curl z in the opposite direction with each other, also curl y and curl y. This is what I need you to understand. So in this way you need to collect the terms, right? Similarly, I'm having the terms with curl x by curl v as, please remember, if I'm having u outside, inside we are having v, right? Similarly, if I'm having v outside, inside we must have u, and then the third term, right? And this complete is nothing but curl f1 by curl v. So this is curl f1 by curl v plus curl x by curl v into, this is curl f1 by curl u. Writing this term first. So this is curl f1 by curl u multiplied with curl x by curl v minus curl f1 by curl v multiplied with curl x by curl u. Marking this as 2. So this is the solution of the first term of the integrand. This is the solution for the first term of the integrand. We have calculated this first term. And by symmetry, I am going to write the results for these two. So these are the three terms of the integrand. We have calculated this first term and now writing the result for the second term by symmetry. So for f1, if I am having here f1, for f2 I am writing curl f2 by curl u into, I am having for f1 x, right? For f2 I must have y. So this is curl y by curl v minus curl f2 by curl v into curl y by curl u. Similarly, writing the third term, curl f3 by curl u into curl z by curl v minus curl f3 by curl v into curl z by curl u. Marking this as 2 and this to be as 3 and this to be as 4, and now I am going to put all these values 2, 3, 4 in 1 here in this main equation. And the left hand side of this is the surface integral of curl of f vector dot product with n vector ds. Right? Okay. So the third part is to substitute the values of 2, 3, 4 in the main equation, that is first one. And outside of this integrand, we are having du dv. Writing this du dv inside. And now in the next step, I'm going to use the Green's theorem over here. If I'm having here du dv, here we are having dx dy, right? Instead of du dv. So we need to compare this with this, right? For this du and curl u, I'm having dx and curl x, right? So I need to have my q to be this one. Similarly, for this p, I must have this p to be this one. That means from this we need to replace dx with du and dy with dv. So the first integrand becomes the line integral of q. If I am having dy here, I have to write dv. Very fine. Plus p, if I am having dx over here, I must write here du over the curve C. Very fine. Okay. So this is q dv plus p du. Let me write here the line integral of Q dV plus P du. And what is Q? It is F1 curl X by curl V. So this is F1 curl X by curl V. And what is P? It is F1 curl X by curl U. Similarly, for the other terms, by Green's theorem, we write, so I'm writing by symmetry the second term. So this is line integral over C. Instead of F1, write F2. And now curl Y by curl V dV plus F2 curl Y by curl U du plus the line integral over C F3 curl Z by curl V dV plus F3 curl Z by curl U du. You may also write these terms having U at the first place and the terms having V to be in the second place. In the next term, I will write like this. So further, this is the line integral over C. I am taking this F1 common from the bracket. So this is F1 into, I am writing the second term first. So this is curl X by curl U du plus curl X by curl V dV plus the line integral over C. So taking F2 common. And then for the third term, taking F3 common. Now see the terms in the bracket. I'm having curl X by curl U du plus curl X by curl V dV. So we need to recall that dx can be written as curl X by curl U du plus curl X by curl V dV. So the term in this bracket is dx. Similarly, the term in this bracket becomes dy and the term in this bracket becomes dz. This is the result I have used over here. So this is line integral over C, writing f1 dx plus f2 dy plus f3 dz. And we can write this as the product of f1i vector plus f2j vector plus f3k vector, taking its dot product with dxi vector plus dyj vector plus dzk vector. Can I write like this? Yes, it is the dot product of these two. So this is equal to the line integral of, this is nothing but your f vector. Very fine. And its dot product with, this is your dr vector. For if r vector to be equal to xi vector, yj vector plus zk vector. Right? So we have shown that what is the left hand side? Yes, do you remember? The line integral over the curve C, dot product of f vector with dr vector. What is on the left hand side? Yes, it is surface integral of curl of f vector dot product with n vector ds. So it is the surface integral of curl of f vector dot product with n vector ds. So this is your Stokes theorem, and finally the Stokes theorem has been proved. Okay, thank you. Stay blessed.